Hello, everyone. Thank you very much for joining us today for the 8th annual meeting of the Innovation for Cool Earth Forum, hosted by the Ministry of Economy, Trade and Industry, and the New Energy and Industrial Technology Development Organization. My name is Nakaya Akiko, serving you as MC for this session. Now, if you have any questions, please submit your question in English from Slido column under the live streaming page of this symposium. However, please note that all questions from Slido may not be answered during this session. Now, let us begin this side event, the NEDO Moonshot R&D Program Symposium, Future Prospect for Direct Air Capture and CO2 Utilization. First, I would like to introduce the two moderators for this session, Dr. Yamaji Kenji and Dr. Yamada Hiroyuki. Dr. Yamaji is a President, Director General of the Research Institute of Innovative Technology for the Earth and Professor Emeritus of the University of Tokyo. And Dr. Yamada is Director General of the Frontier and Moonshot Technology Department of the New Energy and Industrial Technology Development Organization. Now, I would like to ask Dr. Yamada to moderate this session. Dr. Yamada, if you please.
Hello, everyone, everywhere you are. Thank you very much for joining us today for NEDO Moonshot Research and Development Program Symposium, named Future Prospect of Direct Air Capture and Carbon Dioxide Utilization. My name is Yamada Hiroyuki again. Yesterday, researchers, including Japanese, who are studying climate change, were announced to receive the Nobel Prize in Physics. I think that is one piece of evidence that climate change is an important issue. We organized this symposium in the hope that ICEF and our Moonshot project will be a step towards solving climate change issue.
Total of this symposium will be 2 hours and 15 minutes. I'm sorry that it will be late night or early morning for overseas participants, but if you could keep up with me until the end, I will appreciate it very much. First of all, I will introduce outline of Moonshot Research and Development Program and the schedule of this symposium. At first, I will talk about Moonshot R&D program and Moonshot goal number 4, which NEDO is promoting. Moonshot R&D program was set by government of Japan in order to develop radical solutions for difficult societal challenge. In this program, CSTI, Council of Science, Technology and Innovations, set the Moonshot goals. To realize human well-being, 7 Moonshot goals were decided. We have already started these programs. In addition, recently, Moonshot Goal 8 and 9 was set by the government. NEDO is promoting R&D activities of Moonshot Goal 4. Moonshot Goal 4 aims realization of sustainable resource circulation to recover the global environment by 2050. Based on the Moonshot goal, program director and research promotion agencies such as NEDO selected the project managers and R&D projects. We are strongly promoting these projects. Let me introduce our program director, Dr. Yamaji Kenji. He is president of the Research Institute of Innovative Technology for the Earth, we call RITE. And also, Innovation for Cool Earth Forum, this forum, steering committee member. He is an expert of analyzing global warming and energy issue. He is serving in many advisory bodies on energy and environmental policy for Japanese government. And also, he contributed to Intergovernmental Panel on Climate Change, IPCC, as a lead author for third and fourth assessment reports of Working Group 3. In order to realize the Moonshot Goal 4, Dr. Yamaji, our program director, and NEDO embodied the themes of technical development. Specifically, the goal aims implementation of technologies such as direct air capture of carbon dioxide, utilization of CO2, circulation of ultra-thin nitrogen compounds, and decomposition of marine plastic litter in society by 2050. Then we selected 13 projects which correspond to these themes of technical development. In this symposium, 7 project managers who lead the R&D of direct air capture and utilization of CO2, which are shown in blue in this chart, are invited. Next, I'd like to introduce today's program and speakers. This is today's program. First part is a keynote session. Today, we have 3 keynote speakers. First, Dr. Yamaji, our program director. Next, Dr. Graciela Chichurinsky, co-founder and CEO of Global Thermostat LLC. Finally, Dr. Gregory F. Nemeth, professor of the University of Wisconsin. They will deliver the attractive presentation about direct air capture, respectively. Then, in second part, 7 project managers, Dr. Kato from AIST, Dr. Kodama from Kanazawa University, Dr. Sugiyama from the University of Tokyo, Dr. Noguchi from the University of Tokyo too, Dr. Norinaga from Nagoya University, Dr. Fukushima from Tohoku University, and Dr. Fujikawa from Kyushu University will deliver the short presentation. After that, Dr. Yamaji takes the chair and the panel discussion will be done regarding the possible scenarios for the widespread adoption of direct air capture and CO2 utilization. All speakers will join that panel discussion. Unfortunately, Dr. Kodama is inconvenient today and only his short presentation will be streaming. That concludes my presentation. Thank you for your attention. We move to keynote session.
Okay. I'd like to move to keynote session. First speaker is Dr. Yamaji, our program director. Dr. Yamaji sensei, お願いします。
Yes, thank you very much. Could you show my slide? Yes, and I'm Kenji Yamaji, and as Yamada-san introduced, I was appointed as a program director of Moonshot Goal number 4. And it's my pleasure to be given a chance to talk on this symposium. And my title of talk is The Role of DAC in Realizing Carbon Neutrality. By the way, as Yamada-san already mentioned, this year's ICEF has started with a very, very good timing. Yesterday, it was decided that Dr. Manabe is to be awarded Nobel Prize for his climate science studies. And I expect the people's attention on climate change issue will increase much more using this occasion. By the way, go back to my slide. Okay. So I borrowed this slide from my presentation at the International Conference on Carbon Recycling 2021. And that was held on this last Monday, 2 days ago. And as shown here, carbon dioxide recovered from natural gas well or thermal power plants. And that is have been done. And recovered carbon dioxide were injected underground or used for enhanced oil recovery. That has been done. And from the air, biomass, which was made by natural photosynthesis using carbon dioxide in the air, and has been used as fuels and materials. And the challenge of Moonshot goal number 4 is artificial recovery carbon dioxide from air, DAC, and to use that recovered carbon dioxide, so carbon recycling. And this slide was already explained by Yamada-san. So Moonshot goal number 4 challenge is to recover the waste emitted already to the environment and to reuse or detoxify. In the case of carbon dioxide, that means direct air capture and use of the recovered carbon dioxide. And as this is already told by Yamada-san, we adopted 7 DAC projects among the 13 all Moonshot number 4 the projects. That is shown here, but more distinctly this slide. Okay, these are the 7 projects related to DAC and carbon dioxide use under the program of Moonshot goal number 4. So while the contents will be explained more detail by each project managers, outlining that follows. Dr. Kato's project is artificially synthesizing microorganisms that can utilize electric energy. And Dr. Kodama's absorption or capture is solid solvent and honeycomb rotors. And membrane reactor is used for the use of CO2. And Dr. Sugiyama's project, physical absorption and electrochemical CO2 enrichment, and electrolysis used for carbon dioxide use. And Dr. Noguchi's project is mineralization using the carbon dioxide in the air. So waste concrete is used to make calcium carbonate concrete. And Dr. Norinaga's project is pressure swing driven by cryogenic pumping with liquefied natural gas. And recovered carbon dioxide will be used for making carbon neutral methane. And Dr. Fukushima's project is a membrane separation and dual function materials. And dual function materials used for the to make some chemicals from recovered carbon dioxide. And Dr. Fujikawa's project is also membrane separations and electrochemical and some chemical conversion used to use the recovered carbon dioxide. Okay, so already said, but Moonshot goal number 4 challenge is one is DAC to recover carbon dioxide in the air. It's around 400 ppm, very thin. And the second challenge is CCU, recovered carbon dioxide used to either fuels or chemicals or mineralization as a carbonate, calcium carbonate. And the meaning of DAC is shown here. The important role of DAC is to set the upper limit of the cost of carbon dioxide removal. As shown here, the optimum carbon dioxide mitigation should be introduced in the order of lower cost measures. And DAC, direct air capture, once implemented, DAC can capture a huge amount of carbon dioxide. Then, more costly measures, more costly than DAC measures, shown here in green, can be avoided. And if the cost of DAC is reduced by innovations on right-hand side figure, the area of green will be expanded. So in this sense, DAC technology plays as a backstop technology in the climate change mitigation. And another challenge I also mentioned is the use of chemically stable carbon dioxide. Particularly to make fuels from carbon dioxide, we need energy and hydrogen. And in the case of calcium carbonate, chemical reaction is exothermic, that the heat discharging process. But while it is required to confirm whether enough amount of carbon dioxide can be economically used as a measure of climate change. And thus, the life cycle assessment is very important to evaluate direct air capture and carbon dioxide use. We are asking all Moonshot DAC project managers to evaluate net carbon dioxide emission reduction from total process. Okay, it is the last slide. To realize carbon neutrality, we should mobilize various measures from upper right-hand side, various innovations, social innovations using digital technologies. And we should use various carbon-free energy sources. Fossil fuel with CCS can be, how to say, classified as a carbon-free fuel. But since there are several hard-to-abate sectors like steel making, we need negative emissions, including DAC. And we need also carbon recycling and to make carbon-free synthetic fuels, and thus to decarbonize hard-to-abate industry. Thank you very much for your attention.
Thank you, Dr. Yamaji. ありがとうございます、山地先生。Thank you for
Yamaji-san.
explaining your thought of Cool Earth and Moonshot Goal 4 and direct air capture. I'd like to move to second speaker. Second speaker is Dr. Graciela Cicilinsky, co-founder and CEO, Global Thermostat, LLC. Global Thermostat is one of the most successful DAC, direct air capture solution company. And she will present their solution in their solutions in her presentation. Dr. Graciela Cicilinsky, thank you for joining us today. Please listen to Dr. Cicilinsky's presentation.
Good morning. It's a pleasure to be here today. By way of introduction, I am the CEO and the co-founder of Global Thermostat. Our company was introduced in the year 2010 with an unusual purpose to commercially find a solution to reverse climate change. We do so commercializing a technology, a breakthrough technology, that is sometimes called direct air capture, that removes CO2 directly from air and stabilizes it in Earth for the purpose of creating products and services that are commercially cost-effective, which means that the cost of removing the CO2 is lower than what the market will pay for the CO2. Our company has received very significant funding from the Department of Energy and awards, a large number of awards, including the award of being the most fundable company in the United States right now. And this is all happening in real time right now in this year, in the year 2021. The question that many people ask is, why are we removing CO2 from the air? Why not take it, for example, from the chimneys of facilities that emit concentrated 10% CO2? When we take it from air, it's much more diluted. It's 400 parts per million. But this is the only way that we can satisfy the requirements of climate change. By doing it from air, we can avoid transportation costs, because air is distributed over the entire planet uniformly, so wherever you are, if you can remove CO2 from air, you can produce CO2 with no need for transportation, which is the most difficult logistical part of the production and the sale of CO2, and the most expensive. CO2 is as versatile and as valuable as fossil fuels, for example, as petroleum, that can be used for the production of chemicals and for polymers and for fuels. You can now produce polymers and fuels using directly the CO2 molecule instead of the molecule that comes from petroleum. That means that instead of bringing the CO2 from under the earth in the form of petroleum, we now bring it from the atmosphere, bring it down in the form of a gas, CO2. We are in unprecedented times. Indeed, the National Academy of Sciences of the United States and the United Nations Intergovernmental Panel on Climate Change both have documented in recent reports the need for removal of CO2 from the atmosphere as the only way that we can prevent catastrophic climate change now. And please understand that removing the CO2 is actually favorable to the economy if we use it for the products and the services that we described. For example, the cost that we attribute to the removal of CO2 can be below the market price, therefore leading to profits in the removal and the sale of CO2. How much, will you say, is needed? Well, the United Nations projections expect approximately 10 gigatons, which means 10 billion tons of CO2 have to be removed over the next decade or so, and then 30 or 40 over the next 3 decades, in order to be able to prevent the most catastrophic form of climate change. We have an immediate need for low-cost, available CO2 because the supply interruptions are happening today. For example, Heineken declared the need for more CO2 for their beer, but in addition to beverages, there is a number of chemical products as well as materials that require CO2. So the issue here is how to produce the CO2 at the low cost, wherever is needed, and to do it in such a way that you can avoid transportation that is very costly and logistically the most difficult part of the whole equation. A brief summary is that we are currently producing approximately, through the market, approximately 100 million tons of CO2. And for the purposes of reducing and, in fact, reversing climate change, we need to move very quickly in this decade to going from 100 million tons of CO2 to removing 10 gigatons, which is 10 billion, from 100 million to 10 billion. And a quick computation will show that $100, at $100 per ton, we are talking about a $1 trillion market, which is exactly what McKinsey predicts for this decade, which means that this is going to be soon one of the most important markets in terms of profits, in terms of productivity in the world. It has to be understood that CO2 is a very useful, very valuable gas. And McKinsey, for example, reports that in this decade, the market for CO2 is approximately, or is above, $1 trillion per year. And that includes desalination of water, the production of beverages, and even foods, the use for agriculture, such as fertilizers that are not polluting, the production of materials, for example, cement or polymers that are renewable, as well as the use for synthetic fuels, for example, synthetic gasoline that is produced from water and air. What are the advantages of global thermostat technology? From our point of view, they are fundamentally that this is a technology that can resolve climate change. Who says so? The National Academy of Sciences of the United States, the United Nations Intergovernmental Panel on Climate Change. It is known. However, we have to measure what those benefits are. And I think the number one is the fact that we don't need to transport the CO2, which is the most expensive and difficult part of the process of producing and selling CO2, because CO2 can be produced in situ, wherever you are. There is air, and air is the last free public good in the planet. We are contaminating it, producing climate change, and what is being done by global thermostat technology is to clean that contamination, leaving clean air and making the available CO2 lower cost across the world, eliminating pipelines and transportation, which is expensive and very awkward. Our breakthrough technology, global thermostat technology, which has a large number of patents and is in the process of commercializing now, is so low cost because it uses low temperature heat and very minimal amounts of electricity. In fact, if you ask how much energy is used in the process of removing CO2 from the atmosphere, the response is approximately 5 to 10 gigajoules per ton of CO2 that is removed, and that is approximate, and it depends on the design. So low temperature, which makes the process safe and low cost, the fact that we need no transportation, and the fact that we use very little energy otherwise, like 5 to 10 gigajoule per ton, make the process efficient, low cost, and very favorable for environmental purposes. There are two forms that our technology takes. In one of them, we take CO2 directly from air, which was already mentioned, using low temperature, and the air is moved through so-called monoliths, which are 6 by 6 by 6 structures that allow the air to be trapped in its pores for the purposes of taking off the CO2. That's called adsorption. Once that process is completed, then the use of water vapor, which is a way to administer heat, separates the CO2 from the rest of the gases, and out comes a 98.5% pure stream of CO2 at normal pressure. So this is, in a very short form, what the process does. And we have patented some of the key low-cost processes to obtain very efficient form of CO2 produced from air. And one of them, for example, is the use of modular technology, so that we don't need to go to extremely large structures to produce more CO2. We just put several of these modular units together, very similar in that sense as wind energy that is producing windmills. And if you want to produce more energy, you put more windmills, and that decreases the cost and the risk from that of using enormous structures. That's called now scale out instead of scaling up. That's one example of our technology. But there is other examples of what we do. For example, at the Stanford Research Institute, SRI, no longer called Stanford Research Institute, but SRI, in Silicon Valley, California, our plant removes the gases that exit the power plant, which is a natural gas power plant. Those gases are about 7% CO2. The use of those gases allows our system to capture even more CO2 faster and at relatively lower uses of energy with similar processes. Global thermostat technology and its low cost have been tested in laboratories, at the bench, and are now in the process of being tested commercially. And the costs that were described here compare well with the costs that were obtained. There are different embodiments for the technology, but generally speaking, we do have a cost-effective way to remove CO2, and that's what counts. Some of what I'm saying here has to be done very quickly because the time is limited and your attention is greatly appreciated. I suggest that if you have questions, you could read a recently published book that is shown here in this video called Reversing Climate Change. In that book, you will see responses to most of the questions, and you will see a complete presentation of the technology and the policy behind the removal of CO2 from the atmosphere at commercial prices, which is what Global Thermostat does. So in closing, I want to thank the Japanese people and the government for the ability to reach out to you directly, because Japan is one of the most advanced, technologically advanced nations in the world, as you know, and has been extremely valuable in the environmental battles that had to be fought and that continue to be fought. And now we are talking about the biggest one of them all, in which the survival of the human species is at stake, climate change. I should say that I can confirm that we are in very positive discussions with a number of organizations and private companies as well, because of the possibility of cooperation and partnership with Japanese entities. And we are very keen to do that. We hope that this will be very successful, and we thank everybody involved for their interest and for their support, which is very greatly appreciated. We also thank you for listening, because we know your time is valuable, and I can tell you that without you, nothing can be done. So we need you, we thank you, and we look forward to working together with the Japanese people and the government very successfully.
Thank you for your interesting presentation, Dr. Chichirinsky. I will buy your book. And now, regarding your presentation, I'd like to accept questions from participants or audience. We have already received questions from audience via online platform Slido. Please show me that question. Okay. In your presentation, shows the capture cost is $25 per ton. It seems very inexpensive cost. Is the cost including infrastructure cost? Do you understand?
Yes, I don't think I said that the cost was $35 per ton. I don't think it is $35 per ton. So there may be a confusion. I don't think I gave any specific dollar amount.
Okay. And the next question is it totally carbon negative in terms of life cycle assessment? But maybe this question means from life cycle assessment view, your system or idea is carbon negative effective, or you cannot explain yet?
Yes, I understand. The whole purpose of direct air capture is to remove CO2 from the atmosphere, so that the final result is that the atmosphere decreases its concentration of CO2. Before and after, there is a decline in the concentration of CO2. Before you use a technology and after you use a technology. That is the definition of the word carbon negative. And our technology satisfies that property. It does so considering all the elements, including the use of energy, which, as already stated, is approximately between 5 and 10 gigajoules per ton of CO2 that is removed from air. And the way this is achieved, for example, is by using renewable energy like wind that is not emitting CO2, or solar photovoltaic, which, as you know, is the lowest cost of the production of electricity of all energy sources. So either by using, for example, solar photovoltaic energy, or hydrology energy, or by using wind energy, which we do in some of our projects as well, we obtain a carbon negative feature for our technology. meaning that after the use of the technology, you have the atmosphere from where the CO2 is extracted is lower in its concentration of CO2 than it is before. But if you were to use fossil fuels as a source of energy, the result may be different. So it's important the configuration and the design of the technology that you use in order to make sure it is carbon negative.
Thank you for your answer. I understand that renewable energy is very important for carbon negative technology. Thank you very much. Well, other question we have received? No? Okay. Thank you very much, Dr. Chitinsky. I'm very happy to see you. Thank you. I'd like to move to next presentation. Third keynote speaker is Dr. Gregory F. Nemeth, professor of the University of Wisconsin. He joined a session of Moonshot Goal 4 of International Symposium held in December 2019. Thank you very much for joining us again, Dr. Nemeth. His research focus on understanding the process of technological change and public policy which can affect it. He will present his thought on direct air capture in his presentation. Please listen Dr. Nemeth's presentation.
Hello, my name is Greg Nemeth. I'm a professor of public affairs at the University of Wisconsin-Madison in the US. I'm going to be presenting on learning, adoption, and scale-up in carbon removal technologies, and I'll be highlighting some results from a newly initiated project funded by the European Research Council called the Geoengineering and Negative Emissions Pathways in Europe, or GENE. And there's 3 points I would like to make in this presentation. First is that there's an innovation gap in carbon removal technology, and that's really the motivation for some of the work I'll be talking about. Second, there's a need for accelerated models of innovation in carbon removal, and I'll talk a little bit about how we might inform the design of policies to accelerate innovation in carbon removal technologies. And third, I wanted to introduce the notion of dynamic policy support. So the idea here is that we need policy support that is more comprehensive, that takes account of the full set of activities in the innovation process, that is persistent, that creates long-term credible expectations, and thus can support and enable the scale-up and acceleration of carbon removal technologies. So first, on the GENE project. So this is a 6-year project, an ERC synergy grant, and it includes a range of collaborators I'm really excited about working with. That's Benjamin Sovacool from the University of Aarhus in Denmark, Kevon Riahi from the International Institute for Applied Systems Analysis near Vienna, Austria, Jan Minks from the Mercator Research Institute for Global Commons and Climate Change in Berlin, and me from the University of Wisconsin-Madison. What I'm excited about with this project is that it's a comprehensive assessment. It's looking at the technological parameters, it's looking at scale up, it's looking at public acceptance, among other things, and I'll talk a little bit about what we'll do there. I wanted to post a link on the slides to a website that we have. So the project has just started a few months ago. So really in the first few months of a 6-year project, but we have assembled some information about what we're trying to do and especially who the team members are. And that's one of the strongest parts about this endeavor, the team. So I'm sure we'll have much more to present in the coming years as we go deeper and deeper into this important topic. Just to put a little bit of perspective on this work. So the GENIE project is looking at carbon dioxide removal and solar radiation management. So it sometimes goes under this term of geoengineering. And this is where one of the things that I would emphasize here is that CO2 removal and solar radiation management are just parts of the effort to address climate change. There's no sense in which only doing CO2 removal or only doing solar radiation management takes care of the problem on its own. And it's not even true that they take care of most of the problem. We're talking about some part of the problem. For example, with CO2 removal, we might be talking about removing 10 gigatons of CO2 by 2050. And we're currently emitting about 50 gigatons a year. So we're talking about addressing maybe 20% of the problem with CO2 removal. Similar with solar radiation management. We're talking about maybe reducing warming by a degree or more than that. But we're talking about dealing with warming of 2 to 3 degrees in a business as usual case. So it's really only just part of the solution. We need to do other things like decarbonizing energy demand, reducing energy demand, addressing industrial CO2, and also adapting and building resilient communities to deal with climate damages. So there's lots more to do than just CDR and SRM, but they're important tools and we seek to understand them better in this project. So here are the working packages that we've designed here. We've got one on understanding the costs in terms of where they are today and their ability to become less expensive or possibly become more expensive in the future, and also how much we can assess that they might remove. So when I said 10 gigatons in 2050, what does that mean for each carbon removal technology and how can we think about them together? Second is looking at bottlenecks. So what are the sources of constraint on growing carbon removal technologies? Third is on social acceptance. So this is not just a nice to have or an extra part. We see this as an intrinsic part of these technologies scaling up because they'll have to scale up in a quick way over the next 30 years to get to gigatons by 2050. And that's going to require broad public support. And if there is not broad public support, that's likely only to slow down what needs to be a very rapid process. 4 is the focus of my work on learning and adoption. So how can these technologies improve as they become more broadly used? And then how can we spread their adoption more quickly? 5 is on risks. So thinking broadly about the risks to ecosystems, to biodiversity, to water supply, energy supply, land and food prices. All of these technologies will need to be deployed at very large scale to make an impact on climate change. And as a result, we need to take their risks seriously. 6 is trying to inform policy support. So what policies might help accelerate innovation in these technologies. 7 is a work package on synthesizing all of this together. And 8 is what I'm doing right now is talking about the work and making it more accessible to a broader audience. So getting a little bit into the motivation for this work. So the motivation is that we're going to need gigatons of carbon removal by the 2050s. That if you look historically, technologies have taken a long time to scale up. And if we look at where those technologies are today, there is a focus on R&D, which is important, but not sufficient. And what we're really missing is some urgency on post-R&D innovation activities, like creating markets, demonstrations, and creating widespread deployment ultimately. The objectives of this work is to inform the scale up, to specify enablers of acceleration, to identify barriers to the scale up, to assess the timing and the pace of scale up, and that can be helpful for putting it into an integrated assessment modeling framework, which is part of our team effort. And 5th, to find some insights for policy. Okay, so the theoretical basis for this work, I'll just briefly mention it. We're really coming from an innovation systems perspective, studying transitions. We've done some work called the Energy Technology Innovation System, and a couple of insights that come from that work that are relevant here is to think of innovation not just in terms of a research and scientific endeavor, that's a part of it, but that there's a sequence of stages, some of which are on the supply of innovation, demonstrations, and scale up, and some of which are on the demand for innovation. Where are the markets? Who will buy it? Where will the demand come from? And will the public accept and endorse this technology, and that there are important feedbacks throughout the system so that the downstream activities inform the earlier stage activities like scale up and demonstrations might lead to new R&D loci. So none of these efforts ends as we progress from one stage to the other. They're receptive to feedback from later stages. Part of this is informed by economics of innovation. And then another perspective that's important is that on national innovation systems, that the technologies that might be well suited to one country's environment might not be well suited to another. And that might have to do with natural resources, but it also might have to do with the industrial base, the type of government, the complementary infrastructures, education, tolerance towards risk, financing, a variety of other elements that make one country's innovation and adoption different than another. So we want to be explicit about that. So here's this point I mentioned at the beginning about there being an innovation gap. And this was from some work I did with colleagues a couple of years ago where we coded all the papers on carbon removal technologies or negative emissions technologies in this slide here, and coded them by technology and then identified what stage of the innovation process they were most representative of. And you can see here that by far the biggest area on which papers are being published was on R&D, a small amount on demonstrations, some accounting for scale up, and a much smaller amount on the demand side, on niche markets, on demand pull, and on public acceptance. And that's really this gap we see between there being so much effort on R&D and not enough on the downstream side. And if we look on that top panel there and look at how much negative emissions we're going to need starting in 2030, which is only a few years away, and scaling up to gigatons by 2050, we really need to start to get serious about improving these technologies, deploying them on small scale, maybe having some public procurements, and really starting to create a market and demand for them. If they're going to get to gigatons by 2050, that work needs to start soon, and we really need more effort on the demand side of the innovation process. One of the insights too from earlier work, and we'll be using quite a bit of case studies in this work to understand scale up, is looking at the time horizon. So if we look at solar photovoltaics, an unquestionable success, it took 60 years to go from the first commercial solar cell in 1957 to the first power purchase contract that was cheaper than fossil fuels in 2017. If we look at direct air capture and say that first commercial plant was in Switzerland in 2017, that 60 years later, that puts us at low-cost direct air capture at 2077 and then widespread adoption by 2100. That's far too late to deal with climate change, as the slide before talked about. So what we need is this accelerated development pathway so that we have low-cost direct air capture by 2040 and widespread adoption, that is gigatons, by 2060. And even though that seems like a vast acceleration, it's 4 times faster than what happened with solar PV. But we also have examples. So developing a vaccine for COVID-19 under Operation Warp Speed, which included R&D support, but also guaranteed markets, that was 4 times faster than the world record vaccine for measles 50 years ago. So there is the ability, when there's strong consensus, when there's multiple policies, when there's strong funding available, to make innovation happen on the pace that we need to get to gigatons by 2050. In some cases, maybe just 2 times is fast enough. And you can see the scale up of these solar photovoltaic companies from Japan, from Germany, and from China. And those are scale up rates, it's a logarithmic scale there, of 100 to 200% a year. Climeworks had a target of getting to 1% of emissions by 2025. That would have been about a 200% a year increase. They now have a goal of something like a gigaton by 2050 or a megaton by 2030. And that implies a growth rate on the order of 40% a year. So that's sustained longer than any of these PV companies lasted, but it's not at the rate at which they grew when they were growing the fastest. It's considerably lower. So the scale up is possible. We do have historical precedents, and that's a lot of what we're trying to do in this work, is develop a systematic way to understand how technologies have progressed and accelerated in the past, and then to map those to carbon removal technologies. And for direct air capture, for example, there's one category of technologies that is high technology, where there are many iterations, where you might have disruptive production, that is being able to compromise on attributes that don't matter in order to achieve attributes that do matter, like cost. So solid sorbent direct air capture looks a lot like that first category. And so we'll be looking for other case studies to inform the scale up of solid sorbent direct air capture. Liquid sorbent direct air capture with much higher temperatures and much larger scale looks more like bioenergy with carbon capture and sequestration, and we might use chemical plants where system integration is really the challenge. And we have examples of scaling up those quickly in a large way too, but it's a different model. And so what we're doing in this work is finding scale-up models so we can map how we might accelerate things faster. Some of the policy accelerators for this type 1 technology that we'll be looking more into, but just to give an examples of where we're going, is if we wanted faster on these like small scale direct air capture, we'd want technology push ideas like R&D, like training scientists and engineers and public procurement. We'd want to accelerate knowledge exchange by codifying knowledge, having it exchanged from one person to another, company to another, and global mobility accelerates that as well. And then finally, markets that are robust, where there's disruptive production, and then where we take political economy concerns seriously. So one other item I just mentioned in my last few minutes of remarks here is on scalability. And one of the challenges we have, and it might turn out that small technologies could turn out to be more scalable than large ones. So this is a hypothesis we're working with and testing, but you can see some data that show that small technologies have higher learning rates than larger ones do. Smaller technologies improve more quickly. Second, small technologies seem to get adopted more quickly. The time it takes for them to go from 10% of their ultimate market to 90% of their market is much faster at smaller scale. Smaller scale also means more iterations. So we've built more than 1 billion solar panels in the history of the world, 1 million wind turbines, many million electric vehicles. We've not built more than 1,000 nuclear reactors and just a couple dozen of carbon capture plants. So looking at how many iterations is a possibility as well. Another concept we'll be working with is looking at maybe you can have modularity within large units. So this is Carbon Engineering's plan for their first large-scale direct air capture plant. It is large scale. There's only maybe 2 calciners there, but there are many, many contactors. So even within large units, you can have modularity, and that's going to be an important aspect, I think, of large-scale direct air capture becoming exciting and moving quickly. So my conclusion here is that we need to focus our effort on dynamic technologies with small unit size and that have modularity in large units where large has some advantage. And that we need to take advantage of iterative improvement, that is make many, many units and sequentially make each one better than the one before. And also to think about system integration with the local ecosystem, with where we might send the CO2, where we might store it, where we might source power or water or other resources from. I think those are all going to be important efforts as we seek to commercialize, improve, and accelerate the adoption of carbon removal technologies. Thank you.
Thank you, Dr. Nemeth, for your presentation. And now, regarding your presentation, I'd like to accept question from our audience. Maybe we have already received questions via online platform. Could you show me questions? Okay. Your low-cost model is scheduled to release in year 2040. What is the target cost of carbon dioxide capture?
A really good question. We see lots of different estimates on cost, and it's really hard to understand what the cost of a first of a kind or even the fifth or sixth of a kind is, because there's so much fixed cost in R&D at the beginning. So it's really hard to say what the costs are today, but numbers that are in the high hundreds, 500-600, seem realistic to me. And the other thing that I would add is that there are some companies out there which don't see themselves as getting on to a cost reduction curve until about 2030, that the next 8 or 9 years for the rest of this decade, it will be a period of experimentation, of finding different approaches, using different materials, improving processes, and ultimately will be really important is convergence on a dominant design. So using a set configuration and materials that becomes common in the industry. We've seen that with wind turbines that found this upwind 3-blade horizontal axis design. We've seen it with solar panels that converged on crystallized silicon. And once you get to that stage, then cost reductions are really possible. So I think we're probably unlikely to get to that convergence stage until sometime at the end of this decade. And from there, we can start to go on a learning curve, and a learning curve that, as we heard earlier in the presentation, looks maybe something like wind turbines, and that as we build more and more of them, the costs start to come out. But we may not see that cost reduction really starting for quite a few years. We're still in the experimentation stage. But to more directly answer your question, there doesn't seem a reason why we can't get down to $100 per ton of CO2 with direct air capture, with incremental improvements along the way, moving to different materials, different configurations, getting costs out, standardized manufacturing, developing a supply chain with making parts and materials and chemicals exactly for the direct air capture industry. All of that can get the costs out. And yeah, I think talking about $100 per ton is a realistic goal.
Thank you for your answer. $100 per ton is very ambitious target, I think. But we need now our Moonshot project need to strongly promote to your target. Thank you. Thank you very much. And other question? Yes. In your slide of CDR innovation gap, how to determine the publication in several sectors in the R&D stage or in the demand pull stage? Do you understand?
Yes. So we use searching to find papers on carbon dioxide removal, and we found 2,500. And then we read the abstract of every paper manually with humans to identify which type of carbon dioxide removal technology. And so some of them were on direct air capture. And then within each paper, we coded which stages of the innovation process they cover. So whether they talk about scale up or demonstrations or R&D. One thing that so that was all just hand done by reading all these papers. One thing that we're going to do moving forward on this project is the number of publications in this area have expanded dramatically, even in the 3 years since we did that work. And so we'll now be using machine learning tools that can take advantage of the human coding that we did 3 or 4 years ago and start to look for similarities in the words and configurations of ideas to identify those stages on a much broader set of papers going forward. So probably talking about 10,000 or so papers, and also looking at other types of publications like patent data, like Global Thermostat has 61 patents or so, and I think there's a broader set of patents to explore as well. So I think there'll be interesting work coming out of that, what was a handwritten effort, and now using some more sophisticated machine learning tools to identify papers and then understand what part of the innovation process. And I'll be very interested to see if there's been a shift in the last few years.
Thank you for your answer. And do you have a time? No? Okay. Thank you. Please join the panel discussion, and we'd like to continue the discussion. Thank you very much.
Thank you.
Next, we have 7 project managers whose R&D are related to direct air capture solutions. They will present their challenging R&D and goals by short presentations. First speaker is Dr. Kato, Senior Researcher, National Institute of Advanced Industrial Science and Technology, AIST. Please listen Dr. Kato's presentation.
Let me start the introduction of our Moonshot project. The title is Development of a Bioprocess that uses electrical energy to fix atmospheric carbon dioxide. I'm the project manager, Soichiro Kato from National Institute of Advanced Industrial Science and Technology, AIST. I got a PhD in agriculture from University of Tokyo in 2006. After 5 years of postdoctoral positions, I have worked for AIST from 2011. My research areas are applied microbiology and microbiology. My research interests are microbiology metabolisms and application of microbial activities to environmental purification, bioprotection, and so on. Here I show the summary of our project. The purpose of this project is development of an innovative biotechnology for negative emission. This bioprocess utilizes electricity as the energy source to convert atmospheric carbon dioxide into useful organic compounds. We aim to develop a bioprocess that can fix carbon dioxide more than 50 times than plants. The concept of our research is shown here. In the left-hand side, we will make a superbugs using the technologies of synthetic biology. We use Ralstonia eutropha, a well-known bioplastic producer as a platform bacteria. We will develop the basic technology for large-scale genome manipulation and create Ralstonia strains with the abilities to utilize electric energy to uptake and concentrate carbon dioxide inside of the cells, and to fix carbon dioxide with high efficiency. In the right-hand side, we will develop a novel bioreactor that is gas phase reaction reactor. The special feature of this reactor is the bacteria can directly contact two electrodes, gas phase containing carbon dioxide and liquid phase containing nutrients. This new reactor can effectively supply electricity, nutrients, and carbon dioxide to bacteria to maximize the capabilities of these superbugs. The figure is an image of social implementation. Our technology can utilize carbon dioxide from atmosphere, and our technology uses electricity from renewable sources like solar light. And our technology can generate organic compounds, including biopolymers and biofuels. Here I show the timeline for social implementation. By 2022, we aim to achieve the proof of concept. Then by 2025 and 30, we will demonstrate the feasibility by lab-scale and pilot-scale reactors. And as the final goal, we will develop the full system that can contribute to 2% of the target value of negative emission and contribute to 10% of biopolymers and biofuel produced in Japan. That's all. Thank you very much.
Thank you, Dr. Kato, for introducing your unique research using biotechnology. And I'm sorry that this session is no question and answer. Quick to move next speakers. Second speaker is Dr. Kodama, Professor of Kanazawa University. Please listen Dr. Kodama's presentation.
Hello everyone. I'd like to talk about our project, which title is Development of Highly Efficient Direct Air Capture and Carbon Recycling Technologies. This is a collaboration work of Kanazawa University and Research Institute of Innovative Technology for the Earth Right. I'm Akio Kodama, manager of this project. I'd like to start by outlining our developments. Our final target is the establishment of carbon recycling system. In order to achieve this system, we develop a DAC equipped with a rotary type absorber and membrane reactor for CO2 conversion to liquid fuel. Of course, life cycle assessment and economic evaluation for this system is essential. One of the most important things to realize economical DAC is the reduction of its regeneration energy. Wright has developed a novel amine which was succeeded in lowering the binding energy between amine and CO2. In special, a solid solvent impregnated to this amine can be easily regenerated by low temperature heat. Now we are trying to develop innovative amines based on these backgrounds. A DAC should be the acceptable size for society while achieving both low pressure drop and high recovery ratio. For these requirements, we apply a honeycomb rotary TSA. The core technology of this process is amine honeycomb rotor. Most important key of this development is how to supply a sufficient heat for desorption of CO2 by the smallest amount of regeneration air. We employ FT synthesis for the CO2 conversion, but catalyst deactivation and reaction rate reduction by generated water become problem. Also, reaction control is difficult due to restriction of the ASF distribution. To overcome these difficulties, we propose this hybrid membrane reactor. I'd like to finish my presentation by listing our developments and key technologies. I thank you for giving me the time to introduce our project.
Thank you very much for Dr. Kodama's presentation. For introducing R&D consists of a solid solvent and a honeycomb rotor system and so on. And third speaker is Dr. Sugiyama, professor of the University of Tokyo. Please listen to Dr. Sugiyama's presentation.
Hello everyone, I'm Sugiyama at University of Tokyo. Let me introduce our project, Integrated Electrochemical Systems for Scalable CO2 Conversion to Chemical Feedstocks. Here is my background. My specialty is the development of the high-efficiency solar cells and the renewable hydrogen production and CO2 reduction using the semiconductor-related science and technology, and also the construction of the global network of the renewable hydrogen. Our project aims at the capture of the CO2 from dilute environment, such as atmosphere and indoor air, using the physical absorption method, and also the electrochemical condensation using the pH gradient applied by the electrochemical potential. The subsequent CO2 reduction reactor is our core technology, where the development of the catalyst and also the reactor design is very important. And we are also aiming at the integration of all the elementary technology into an entire system, from the capture of the CO2 to the production of the high-value materials. The difficulty of the CO2 electrochemical reduction exists in the proximity of the redox potentials for different reactions, and also the necessity of the multiple electrons, which yields the difficulty of the product selectivity and the enhancement of the reaction rate. To mitigate those problems, it is important to design a mesopolar structure which draws the best potential of the copper catalyst. And we have been able to convert almost 80% of the CO2 into useful hydrocarbons by an appropriate design of such a mesopolar structure. Our CO2 capture technology can be implemented as the direct air capture, and also can be implemented for the capture of the CO2 from the indoor air in buildings. This is possible by the scalable size of our CO2 capture technology and is beneficial for reducing the air ventilation and saving the energy for air conditioning. The captured CO2 can be transported to the reduction plant of the CO2 and the succeeding some chemical process. And this plant size is also scalable owing to the electrochemical technology. And the product high-value materials will be used as green chemicals. The major decarbonization technology, energy saving, renewable electricity, and CO2-free hydrogen will have some missing zone. And our technology will fill in this missing zone and will reduce the 100 million ton per year CO2 emission in 2050 and contribute to the complete decarbonization. Thank you for your attention.
Thank you, Dr. Sugiyama, for introducing your research, scalable integrated electrochemical systems. Next speaker is Dr. Noguchi, professor of the University of Tokyo. Please listen to Dr. Noguchi's presentation.
I am a professor at the University of Tokyo and in charge of a project manager of C4S Research and Development Project. Participating institute includes 5 universities and 3 companies. I am chairing ISO TC71 SD8, and my research interest includes carbon neutral concrete, sustainable recycling construction industries, and so on. Cement concrete is an indispensable construction material, but cement production uses a large amount of limestone and emits a large amount of carbon dioxide. 55 billion tons of carbon dioxide in the atmosphere have been emitted due to the decarboxylation during cement production. Annually, more than 2 billion tons is emitted due to the decarboxylation. In C4S, carbon dioxide and concrete waste are raw materials to produce calcium carbonate concrete, CCC. Carbon dioxide released into the atmosphere and calcium oxide remained in the concrete are ubiquitous, and they combine again to form calcium carbonate. The project comprises of 3 sub-projects: production of CCC, production of CCC raw materials, and practical implementation. Concrete waste powder is put into the water and air bubbles up raw into the water to produce calcium bicarbonate solution. The solution is flowed between the concrete waste particles in the container, and then calcium carbonate crystals are precipitated by controlling temperature, pH, and evaporation rate. The calcium carbonate combines the particles to form CCC. Conventional concrete emits more than 250 kg carbon dioxide per cubic meter of concrete. On the other hand, CCC can absorb more than 120 kg. CCC has completely different hardening mechanism, become carbon negative, realize local production for local utilization, and completely recyclable. The goals of our project are to construct several low-rise buildings by 2030 and to make 50% of concrete structures CCC in 2050. As a result, 2.5 billion tons of carbon dioxide are captured, utilized, and stored in CCC by 2050, and concrete will become carbon neutral material like wood. Thank you very much for your kind attention.
Thank you, Dr. Noguchi, for your introducing unique research, calcium carbonate concrete. Next speaker is Dr. Norinaga, Director of Nagoya University. Please listen his presentation.
My name is Koyo Norinaga, Nagoya University, one of the project managers of this Moonshot project for direct air capture. Our project is a direct air capture using cold energy. We call this technology as cryodeck. The process we are proposing aims to reduce energy required for CO2 capturing by utilizing the cold heat of liquefied natural gas, LNG, which Japan imports about 80 million tons annually. But so far, the cold energy of LNG are not well utilized but wasted. Our team consists of not only Nagoya University, but also Toho Gas, Tokyo University of Science, the University of Tokyo, and Chukyo University. This is our proposed process. We first capture CO2 from the air with an absorbent liquid. Then this liquid is transferred to this dissolver. Then, in this sublimation tank, the latent heat of LNG is exchanged with CO2 to convert CO2 gas into CO2 solid, dry ice. As a consequence, the pressure of the dissolver connected to this tank is reduced, and CO2 is released from the liquid and collected. So this is based on the conventional chemical absorption methods, but the chemical absorption method is usually operated by temperature swing. On the other hand, our process is operated by cryogenic pumping, namely pressure swing absorption, pressure swing amine process. So we need no additional thermal energy to heat the liquid, as we always have in the traditional CO2 capturing process. Then we can think that this method has the potential to save energy a lot. One of the advantages of this technology is that CO2 can be recovered as dry ice or liquefied CO2. Then we can warm up it in the closed system. We can generate high-pressure CO2 that is exactly what is desired in the subsequent CO2 storage and utilization processes. We can get high-pressure CO2 without energy for compression. So we look forward to install this process near LNG terminal, and we hope that we can have this technology not only in Japan, but also other countries who import a lot of LNG. Thank you for your kind attention.
Thank you, Dr. Norinaga. Next speaker is Dr. Fukushima, professor of Tohoku University. Please listen his presentation.
Hello, this is Yasuhiro Fukushima, leading a research team of chemical engineers, catalyst scientists, and industrial ecologists from these 4 institutes. Here, I'm going to quickly guide you to the key points of our quest towards utilization of atmospheric CO2 in chemicals production. Many of the chemical products around us contain carbon. For a carbon-neutral future, chemical industries must source the carbon predominantly from 3 recycling routes, from biomass, carbon fixation, and end-of-life products. In this project, we develop a new class of CO2 utilization processes that will allow carbon to be introduced into chemical production through an energy-saving conversion route, which is suitable for use with the above 3 carbon sources. Here are our 2 signature strategies. Strategy 1, taking an energy-saving conversion route. Many chemical substances contain a structure called carbonyl. There are many good examples of carbonyl-containing products around us. The advantage of employing a route that allows CO2 to be used as a carbonyl source is that, by use of an appropriate catalyst, CO2 can be incorporated into the chemical structure without the need for a carbon reduction process. This amounts to a high energy saving. Strategy 2, streamlining the conversion process using DFMs. To obtain CO2, which exists in the air at a concentration of only around 0.04%, in a limited space, at an economically practical production pace, a huge amount of air needs to be blown into the converter as the first step. To save energy here, a high recovery rate of CO2 from the introduced air is the key point. We approached this challenge by adapting membrane separation technology that was originally developed for space applications. In addition, we eliminate the energy requirement for CO2 recovery from absorbents, the bottleneck in the current recovery technology, by using dual-function materials. In one method, CO2 is absorbed by a raw material that simultaneously functions as an absorbent. In another method, a catalyst that also functions as an adsorbent for CO2 capture is used. To streamline the CO2 utilization routes, several methods and DFMs have potential for use. The pioneering process from our project will be producing a urea derivative. The basic method involves bringing the amine that chemically absorbs CO2 into contact with the catalyst. The knowledge on absorption, and the reaction of DFM and CO2 obtained in this work, together with the new simulation and evaluation techniques we develop, will expand the range of carbonyl compounds that can be produced from CO2 with biomass and recycled end-of-life products. Thank you for your attention.
Thank you, Dr. Fujikawa. Finally, next speaker is last speaker, Dr. Fujikawa, Professor of Kyushu University. Please listen to Dr. Fujikawa's presentation.
Hello, everyone. My name is Shigenori Fujikawa, who is the project manager of this Moonshot project entitled in the development of global CO2 recycling technology towards beyond zero emission. First of all, I'd like to briefly introduce by myself. My name is Shigenori Fujikawa. I'm a professor in the International Institute for the Carbon Neutral Energy Research, Kyushu University, Japan. And also, I'm served as a director in the Research Center of Negative Emission Technology, Kyushu University. My research interests are nanomaterial chemistry, surface science, and membrane science. Actually, my current research is focusing on the direct air capture by nanomembrane. CO2 capture directly from air is one of the important technologies to solve the global warming issue. Although there have been many reports to capture CO2 directly from air, there are still problems which should be improved and solved for the deployment of the real world. Recently, we have achieved ultra-fast CO2 permeation by freestanding membrane. Here is our developed freestanding nanomembrane here. Our developed nanomembrane with a thickness of only 34 nanometer shows 40,000 of the CO2 permeance in GPU, which is 20 or 30 times higher than the CO2 permeance reported in the past, without losing CO2 nitrogen selectivity. Based on this result, we think we could capture CO2 directly from air by membrane system. In addition, our project member, Professor Miho Yamauchi in the Kyushu University and Professor Paul Kenneth in the University of Illinois Urbana-Champaign has developed the electrochemical conversion system of the CO2. Especially Professor Miho Yamauchi has developed the nanoparticle catalyst for CO2 conversion, and also Professor Paul Kenneth has developed the electrochemical conversion system to convert the CO2 to the methane, ethylene, or ethanol carbon monoxide. Based on these key technologies, our Moonshot project is aiming at development of direct air capture and utilization as in shown here. First, membrane can separate the CO2 selectively and capture CO2 directly transferred to the conversion system to convert the CO2 to the other useful chemical compound. Especially, our project is aiming at the creation of the decentralized system of our dark unit. As you can see here, our small dark units are distributed in the city area, then to capture CO2 directly from the air and convert it to the useful compound. And this converted CO2 is circulate in the city area. we think this system can contribute to local production and local consumption of the carbon recycle society. Thank you very much for your kind attention.
Thank you, Dr. Fujikawa. Following presentation of project managers, we will have a panel discussion regarding possible scenarios of direct air capture and its utilization of carbon dioxide. And Dr. Yamaji will act as chairperson of this panel discussion. I'd like to hand it over the microphone to Yamaji sensei. よろしくお願いします。
Well, thank you very much. So let me start panel discussions. And the speakers are 8 to my understanding, including myself. And very unfortunately, we were informed that Dr. Chichirunitsky cannot attend this panel discussions. But time is very much limited. It is indicated in front of me, 43 minutes from now. So, okay, but 8 speakers, including myself. So please respond concisely. And I think, including Dr. Nemeth, I think you have some preliminary questions from the Secretariat. First round, I like to confirm that the questions and the answers. So question 1 is what are the possible scenarios for widespread adoption of DAC, including utilization of the recovered carbon dioxide? And how much should the DAC cost go down? This is already discussed in the previous keynote sessions, but I'd like to have your comments. And how can you achieve that cost? So, Dr. Nemeth, could you take a role of icebreaker to have a first speaker to responding to this question? Dr. Nemeth, please.
Sure, I'd be happy to, and thank you for the question. Yeah, I mean, that's one thing that I think, really started to get interested in about 5 years ago with the Intergovernmental Panel on Climate Change Special Report on 1.5 degrees, which was in response to the Paris Agreement to achieve 2 degrees temperature warming and make efforts for 1.5. And the scenarios that were newly developed to figure out what would be required for 1.5 had a lot of carbon removal in them. And so that's led to a lot of research since then to understand what the potential is for carbon removal and the timing for its deployment. And so I think we have a pretty clear picture at this point of at least the order of magnitude of what we'd be talking about. And that is of scaling up from a couple dozen pilot plants, that's what we have today in 2021, to something like a few megatons, maybe 10 megatons, something like that by the end of the decade, by 2030. And then scaling up to gigatons by 2050, and possibly many gigatons from DAC, maybe on the order of between 1 and 10 gigatons per year, and then continuing to grow, maybe more slowly, but continuing to grow and remove CO2 for the rest of the century. But the 2020 to 2050 period is the period of scale up. And we've been doing some work on this recently to get from where we are today to a gigaton for a company of DAC by 2050, or say 4 gigatons for the whole industry, is a growth rate of about 40% over the next 30 or 29 years. So that's a high rate of growth. That means we're doubling the industry in less than 2 years. Every 2 years, so that's many doublings between now and 2050. But that's the type of growth that we've seen in industries before. We've seen the solar industry growing at above 30% a year for the last 30 years. If we did that with direct air capture for the next 30 years, we'd be very close to a gigaton of removal by 2050. And if we were able to go a little bit faster with some of the intentional acceleration and supporting innovation more broadly, there's no reason we couldn't get to 5 gigatons of removal or 10 gigatons of removal by 2050. That gets us from, say, 30% growth to 40% growth. It takes commitment to sustain that growth over time. It takes policy support. It takes, crucially, expectations that there'll be markets in the future. And that's what leads investors to lend money for the scale up. That's what leads supply chain components to design particular solvents and other chemicals and materials and parts specifically for the direct air capture market. And so if there are expectations that there is a market and there will be in the future and that it's growing, we can do, direct air capture can do what solar has done and grow at 30% over 30 years and maybe even do a bit better. If we do that, we're at gigatons. So that's, I think that pathway is not inevitable. Like if we decide not to support it, we won't get to gigatons. But there's nothing imaginary or impossible about it because we've done it before with other technologies. And so I think we could do it with DAC as well if we have the support and the consensus and the persistence to pursue that goal for the next 3 decades.
Well, thank you very much. And unfortunately, I can't see the faces of the participants of this panel discussion, so I cannot identify your responses. But I'd like to invite the responses to my question from the project managers of Moonshot Goal 4, the DAC-related project. But there are 6 project managers are joining this discussion session. So, okay, for the first round, I like to ask each project managers to respond to these first questions. How about Dr. Kato? Can you hear me?
Yes. Okay, our technology is the bioprocess that can fix carbon dioxide and to make the organic compound. Actually, our system is actually not so good for the amount of carbon dioxide fixed comparing to the other DAC system, maybe using the chemical system. But our merit is the merit of our process is we can make the various types of organic compound, including biopolymers, biofuels, and even food. So now our project is in the preliminary step, but yeah, we believe our system is applicable to the message. We can supply such various compound. Yeah, that's all.
Okay. How about Dr. Sugiyama?
Thank you for giving me a chance to respond to the question.
In my back, your face is appears. Okay. I'm sorry, I can't see you.
I'm just standing behind you. Sorry for that. Okay, so let me just state my own opinion. First, I think that the question is mostly for the DAC DAC, right? But I guess that we first need to think about the entire cycle, starting from the capture, the utilization, the conversion of the CO2 to use for substances, and also its way of the utilization. And regarding that, for example, in my case, we are aiming at the reduction of the CO2 to the ethylene, for example, as an example of the useful chemical feedstock. And that actually needs quite a huge energy input in the process of that electrolysis to convert CO2 to hydrocarbons. And compared to that, at least in terms of the free energy change, the energy input to capture CO2 to the condensed form close to 100% is much smaller in terms of the energy input. That means that we rather need to focus on the development of the very nice technology or the energy efficient viable technology for converting CO2 to usable chemical substances, including food products if possible, rather than just focusing on the DAC process.
or contrary, if that downstream process of the CO2 utilization becomes feasible, then my belief is that the capture process has a lot of the possibility, not only the capture from the from the air itself, but also, as we are proposing, the capture of the CO2 from some indoor environment where we already have some good air circulation system, which can be effectively converted to the CO2 capture system as well. So that's my opinion. Thank you.
Thank you very much. So next, Dr. Noguchi, please.
Thank you for giving a chance of the answer. My project is a little bit different from others because our target, the final target, is to utilize the carbon dioxide in the mineralization, such as concrete. But the scenario for the effective carbon utilization, carbon capture and utilization as a raw material of the concrete is one promising technology, because the concrete carbon dioxide is anywhere in air, and also concrete is the second most consumed substance on Earth after water. So it is the reason why we can select the concrete for the carbon capturing materials, and anywhere you can see the concrete. So the one scenario for the carbon dioxide removal from the air, we can establish the factory anywhere in the world if we have a concrete near by your side. And but the problem is in the cost, because the concrete is very cheap materials. We have to provide the concrete in under such prices. For example, 1 cubic meter of concrete, the cost is $100. So I think that 1 ton of carbon dioxide should be less than 25 or 30 US dollars. Such kind of the carbon dioxide should be provided for us to make a new concrete. And we are using the air, from the air, the carbon dioxide is poured in the water and bubbling to produce calcium bicarbonate solution. It's a raw material for the calcium carbonate concrete, and the cost reduction is also in the production time. So we have to provide the concrete from the production rate should be kept. So the production time is very important for us. So that it also lead to the cost reduction. Production time is less than current condition. The cost also be reduced. Okay, thank you. That's my answer.
Thank you very much. Then Dr. Norinaga, please.
Okay. Thank you very much for giving me opportunity to talk my opinion. So here, all of us here are presented here, maybe, so the deck can be the last 1 mile to achieve zero emission of our society. To make the deck to be widely accepted, so in particular Japan, so where we have limited space for the CO2 storage, I believe that the utilization of CO2, for example, carbon neutral methane, can be synthesized by blue or green hydrogen, can be one of the possible scenarios to realize carbon circulation. However, as we know, the drawback of the deck is its cost. And our proposed system, so we propose cryo deck, that uses the cold of liquefied natural gas and has the potential to reduce the cost and expected. And also it is expected to be adopted at not only Japan, but also all other liquefied natural gas LNG importing countries. And from the cost analysis for the absorption type deck, their OPEX operation costs are dominated by two factors that are power for air blowing to the absorber and heat supplied to the dissolver. To minimize the cost of our proposed process, we need to develop technology to reduce the pressure drop in the air contactor, and we need to develop our new process cryodeck that uses LNG cold to realize pressure swing CO2 desorption that can be driven by the cryogenic pumping induced by the CO2 sublimation. So we need non-thermal energy input at all. And then we also have to think about the capex. It is also important issue. So we will be able to reduce the cost by design and structure optimization and also standardization. And also as well as mass production effects we need to expect. Thank you.
Oh, thank you very much. Then Dr. Fukushima, please.
Thank you very much for the opportunity to express my opinion here. I think Professor Yamaji and Professor Nemeth gave really good keynote to the session, and my answers will be well aligned with their direction, I think. My technology is expected to work in the chemicals industry, and Dr. Nemeth, Professor Nemeth already mentioned that if in the chemicals industry use, integration will be a key point. So my process is aimed at very nice integration with the chemicals production processes, namely for the chemical compounds that contains a carbonyl group of chemicals. Now, the possible scenarios for widespread adoption will be, first introduced into the expensive chemicals production process, and then acquire some experience from this implementation, and then move down to a more less expensive chemicals production processes. That would be so simultaneously acquiring experience and also acquiring the fundamental knowledge that will allow us to extend this the same technology, same module to other chemicals production. That will be our strategy. Now, the point is that we start from really expensive chemicals and then to the cheaper ones. So our initial target will be something that will be used for like pharmaceuticals or also some other expensive type of chemical, which is one of the chemical is ethylene urea, and we already have the basic conceptual proof for producing this kind of chemical using the dual function materials and the CO2. So that's my answer to the questions from the Secretariat. Thank you very much.
Oh, thank you very much. So lastly, Dr. Fujikawa, please.
Okay, thank you very much for giving me my to tell my comment and opinion answer. Actually, I'm the last person to answer. That is why most of what has been already explained in many panelists or Dr. Nemeth. But actually, my idea is very similar to the Professor Sugiyama because we have to consider all of the process, including the direct air capture to the final use. In that sense, it is rather hard to answer what is the cost of the duct system, honestly speaking, because there are so many scenarios. But also our technology, especially I am Japanese, that is why I'd like to consider first Japan's situation, because Japan land is very limited. That is why we have to utilize a small area for such kind of system. That is why as Dr. Nemeth said, a small unit, a small system is useful, especially beneficial for Japan situation. And also, I'm looking forward, we are aiming to install our DAC system into the urban city area, because urban city area has a large amount of emit of the large amount of CO2. That is why, from the viewpoint of technology, another high concentration of the CO2 can be easily separated from the atmosphere, especially in office area or school, or say even in a home. Actually, today I measured my I measured CO2 concentration in my bedroom. Actually, it reached 2,000 ppm because I closed everything. In that case, from this viewpoint, such kind of space is very useful for and a very attractive source of the CO2 capture. For this purpose, I think very friendly, very easily installed system is effective, I believe. In that sense, membrane system is one of the key technology to separate CO2 from air safely and easily. But in that case, that is why we are trying to develop the very thin membrane to separate the CO2 from the air very efficiently. At the same time, also, we have to consider the situation about the after CO2 capture. In our project, we are trying to develop the CO2. We are trying to develop the electrochemical or some chemical conversion of CO2 to produce a value-added compound, especially focusing on the daily use. In that sense, we have a pipeline, gas pipeline in the downtown area. So that is why even we have excess, we produce excess amount of methane gas, for example, from the direct captured CO2. We can circulate such kind of methane product, for example, in the downtown or urban city area. That is why such kind of scenario is possible, I believe. That is why we think the simple cost argument is not that difficult, but there is so many arguments or discussion about the cost of DAC. So of course that is still high. I think that is why we have to become more. We have to achieve a lower cost. Let's not say $100 something, $200 something like that. That is my comment. Thank you very much.
Oh, thank you very much. Thank you very much. It was interesting. Some speakers mentioned concrete numbers for the DAC cost target. Okay, let me move to the second question. Second question is regarding the utilization of carbon dioxide captured by DAC. And the question is, what kind of measures are effective in expanding the application of recovered carbon dioxide use? Okay, so again, Dr. Nemeth, could you take the role of the first speaker for these questions?
Sure, I'm happy to. Thanks for the question, but I'm actually really interested to hear about each of the program leaders, because those sound like really interesting applications that they've thought about. But I guess I would say a couple of things about utilization. One is that there are kind of natural markets that exist already where they're not maybe very big, but some of them pay a lot for CO2 and could value a stream of pure or relatively pure CO2. And so we've heard about feedstock in the chemical industry. We have some markets already where it's being used in the beverage industry, which you could imagine is expensive to access CO2 on maybe island situations and things like that, or not close to a chemical plant. So there are some applications. They're not huge, and they're not maybe long-term sequestration of the carbon that is removed. So they're only just a bridge to get somewhere. But in the longer term, after those small but useful niche markets, we can start to think about policy having to play a role here of potentially requiring some sequestration of CO2 or providing incentives for CO2 that's used and put into products. And then finally, the last aspect of, I think increasingly there's more and more attention as to the permanence of the sequestration. And there's a variety of applications in which the CO2 might not be permanent at all, but maybe is okay because it displaces a fossil fuel, for example, like in an electric fuel. or where it is completely permanent, like the concrete example that we had before. And so that's probably going to end up being a pretty important determinant of the value of CO2 utilization, is the longevity of the carbon and the extent to which it stays out of the atmosphere. But I'm most interested to hear what the others on the panel have to say about this.
Thank you very much. So taking the same order of the responses to the first question, so let's start, Dr. Kato, please.
Yes. Okay, again, the merit of using biotechnology, bioprocess is, yeah, we can make various types of organic compound. So I think we need to consider how we can produce various useful substances using our biotechnology system. Yeah, that's all.
Thank you very much. Then Dr. Sugiyama, please.
Okay, yes. So I think that we should refer to the case of the hydrogen, because the hydrogen is certainly a major driver for decarbonization, and the CO2 follows that, in my opinion. So in that sense, we should notice what is happening as for hydrogen. And in the discussion about the hydrogen, the world is going to be so keen about the total CO2 footprint of the hydrogen, which includes the consideration of the life cycle. So in that sense, now the world is trying to make some labeling of the hydrogen, whether this is coming from the fossil sources, and low carbon fossil originated hydrogen is blue hydrogen, and also the renewable based hydrogen, green hydrogen. And as well as that, we may have some quantitative footprint of the CO2 levels to hydrogen in a very near future. Otherwise, we are unable to implement the carbon pricing or carbon taxing system related to hydrogen. Then probably similar discussion, in my opinion, will be associated with the CO2-driven products. For example, if we are going to use the ethylene for the chemical raw material for further stage of the green products, like, I don't know, the green plastics or any other green fuels, then we probably have some label attached to that product, which is the carbon footprint. So in that sense, my conclusion is that how can we secure the traceability of the CO2 footprint related to any product originating from the air captured CO2 or any other recycled CO2? So that is probably the ethical point of view, but also the economical point of view. Thank you.
Okay, some little communication trouble happened, but okay. So Dr. Noguchi, please.
Thank you for the next question. As previously I mentioned, one candidate is the concrete for the utilization of carbon dioxide captured from the air. But I am anxious about the corresponding materials, corresponding substances to the carbon dioxide for the mineralization. One candidate is a calcium, so that we can make a calcium carbonate concrete using the carbon dioxide and calcium in the concrete. But nowadays, we are competing the collection and obtaining the calcium or other minerals such as magnesium. So we need to, for the mineralization, it is probably the very promising CCU technology, because the calcium carbonate has a low energy status, so it is very stable. And so my answer is that one candidate to the mineralization as a concrete, but we are rating of the corresponding substances. That's all.
Thank you very much. So Dr. Norinaga, please.
Okay, thank you very much for giving me the opportunity to think about what kind of measures are effective in expanding the application of the deck and CO2 utilization collected by the decks. Okay, so we think that installing a deck in the local carbon neutral network, which locally produces and consumes, for example, carbon neutral methane, can be one of the possible options in promoting widespread use of our cryodeck. So because this has a high affinity with already existing urban gas pipelines, and we will be able to minimize additional investment for the infrastructure. A rational or reasonable decision will be made, and this is strongly dependent on the affinity with the existing installation environment. This is my opinion. That's a little bit conservative. Okay, thank you very much.
Thank you very much. Then Dr. Fukushima, please.
Hello, thank you very much. I think, I would like to kind of add on to Professor Norinaga's comment. Where we have to think about this existing situations, but also we also need to focus on the future situations. And in the future situations, we would definitely have much less, if not zero, fossil carbon sources being burned for energy. So there will be less CO2 sources like that. And we will be using more biomass or end-of-life plastics recycled to produce things. And the CO2 utilization must be integrated or go align with those processes in the future. And for that kind of processes, it would be distributed all over because it's very costly to bring all the plastics being used to one place, or also the same for the biomass. So those processes will be more distributed in the industries or all around the region, and the characteristics of DAC being versatile. I think this goes well aligned with this kind of setting in the future. So I think not only thinking about the current cost, but based on the vision that we want to realize in the future, I think the policy support for this kind of investment will be very crucial in expanding the application of the DAC systems in general. Thank you very much.
Thank you very much. Then Dr. Fujikawa, please.
Okay, thank you very much. Actually, as Professor Sugiyama said, first of all, the people has to recognize kind of say CO2 footprint. So in that sense, it's better to label something like a system unnecessary. And also, of course, as people generally saying, to accelerate such kind of system, of course, governmental support or say order may be necessary, such as a penalty or incentive system are necessary in general, I guess. And also, I have a collaboration with some art and science department in Kyushu University, and I asked the student to propose the idea to utilize the DAC system in our society, in our daily life. And then they propose many interesting system. For example, say they put something like a DAC system in the vending machine to capture CO2. And also they can, they propose something like a soda to use to utilize capture CO2, and or even they can they propose something like a pet bottle system, pet bottle in a vending machine, and then to use CO2 as some pet bottle source. Of course, this is technically very difficult, but idea itself is good. So that is why such kind of activity, for example, to collect the unique idea from the say many people, also accelerate and change the people's mindset. Such kind of activity also necessary. This is my opinion. Thank you very much.
Thank you very much. Okay, so these are the just end of the 2 round. Is there any questions from the audience? There will be no message, so may I understand that there is no specific questions? Okay. Okay, 2 questions to project managers. What is the target scale of low-cost DAC plant? Is there any bottleneck to scale up your technology? Okay, that can be applicable all projects. So in the order of the same order from Dr. Kato, I'd like to request your response to this question.
Yes. Yeah, actually, our project in the stage of proof of concept. So, I mean, it's quite difficult to consider the scale up and so on. So, but our system is using the kind of electrode and catalyst as the microbes. We have the experience to make the pilot scale reactor for such kind of system for the microbial electricity production, but not to carbon dioxide fixation. So, yeah, I mean, we have some experience to the scale up of such biosystem. So, yeah, I think, yeah, we can develop such large scale bioreactor, I think. Yeah, that's all.
Thank you. Then Dr. Sugiyama, please.
Yes. So talking about the scale, I think, of course, we need to finally aim at the very large scale plant so that we can process the vital amount of the CO2 to be recycled in order to achieve the real carbon neutrality. But in the process of the implementation to the society, I think that we have quite a wide variety of the time difference. So in that kind of the discussion, I think the initial implementation may start from the rather the special case, like the installation to the some building complex, like the Tokyo metropolitan area or the Osaka metropolitan area, of course, New York, for example, so that the we can allow some initially high cost for that a DAC and a carbon recycling system installation. So in that sense, what is important for any technology aiming at the DAC and succeed in the carbon recycle might be scalability. And in some cases, we need to differentiate the systems for the small scale implementation, large scale implementation. But probably the early development may aim at such a scalable technology. And in that sense, of course, that has quite a difficulty because we need to circulate quite a large amount of the air so that we can take the necessary amount of the CO2. In that sense, in principle, the capture process is very hard to be scalable. But my expectation is that the integration with some existing air conditioning system and the already very integrated residential office area might be, say, good target of the initial implementation. And the succeeding conversion of the CO2 to the usable chemicals might be more or less scalable, of course, dependent on technology, but at least our approach of the electrochemical method is quite scalable. So in that sense, my conclusion is that the scalability is very important. And also, we need to, again, identify some good initial target of the implementation, which might be rather for the small scale and also for the urban area. Thank you.
Thank you very much. So then, Dr. Noguchi, please.
Okay, thank you. Scaling up is the very important issue for also our project, the concrete utilization of the captured carbon dioxide. I have already mentioned the corresponding material is a concrete waste. it will be generated in the urban area. And we can use such concrete, new concrete, made from the carbon dioxide and waste concrete, in also the urban area. So regional production or the regional utilization is a very important concept for the carbon utilization. And the bottleneck is, of course, we need such a large area. For example, that in Tokyo or metropolitan area, we have, fortunately, the Bay, Tokyo Bay. We can establish such kind of the area, which is where we can install the plant, and such as waste disposal area also need such big area. So we need an area in the urban, near the urban area. It's our bottleneck of the scaling up of the plant. That's all.
Thank you. So Dr. Norinaga, please.
Okay, thank you for giving me the opportunity to talk about how much scale we have to achieve by using the DAC system. So my answer is very a little bit conservative, but so in the commercial CO2 capture process, we have to use the scale merit or the capex. So in the capex, we need to reduce the capex on the cost of the CO2 capturing. So we have to, we do not aiming at, but we have to make the scale as large as around 1 million ton per year of the DEX as similar with their other commercial CO2 capturing process. So we also have to looking at how to scale up our process. So for the DEC process, one of the drawbacks is we have to treat a huge amount of the air. So that's why we need a large absorber. So we have to reduce the cost. Especially we have to design the absorber air conductor, which minimize the pressure drops to reduce the blowing power. So that's one of the issues. And in particular, our process, we have to utilize the cold heat. So that's why we need to make new types of the solvent, which can absorb very low diluted CO2 included in the air. And the solvent can capture such a low concentration CO2, and then CO2 have to release in the depressurized condition, in the vacuum condition. So we have to find such a very good solvent which can capture and release CO2 at low pressure. And also we have to make the new design for how to transfer the LNG cold to the for the sublimation process of the CO2. That's also a technological challenge we have. So thank you for the question.
Thank you very much. But the time is limited. We have only less than 2 minutes, so please make it short. Dr. Fukushima, please.
Okay, so in our case, we plan to utilize the CO2 in the chemicals industry. And in that case, the problem would be how quickly can we replace the existing chemical plants? Because usually the chemical plants are like long lifetime, 30 years, 40 years. So even though utilization of CO2 has an advantage, maybe if we don't have very, very big margin of improvement, they won't consider earlier replacement. So that might be one of the bottleneck, the replacement of the existing processes. Thank you.
Thank you. So Dr. Fujikawa, please.
Okay, I have just 1 minute, Okay, and actually, so I basically agree with Professor Sugiyama's work, and also what I would say. I forgot to say something, but anyway, so our system is very similar to the photovoltaic system. That is why, in my case, in our case, the scale up meaning is the increasing of number of the unit. In such case, we have to it's better to consider the situation about photovoltaic system deployment. So such kind of support or incentive are necessary. And also, in addition to this, we have to consider about the regulation issue or something LC issue at the same time. Otherwise, because our system will be installed in the urban area, that is why such kind of aspect also necessary. Thank you very much.
Thank you very much. And just we are going over the time limit, but there is one question from the audience. Do you think it appropriate to commercialize DAC here in Japan, or do it in other countries? You can access cheaper renewable energy and sell carbon credit. Okay, the Moonshot program is supported by Japanese government, but output can be applied to globally, I think. And our Moonshot goal is set at 2050 and the social implementation. And in that stage, the output of Moonshot research and development is applied to all over the world, I hope. So that closes panel discussion session. Thank you very much for the participants.